Let's look at how our idea of the atom grew over time. What makes one element different from another? Why some atoms are slightly heavier? How the elements are organized like a giant periodic family, and how we classify them. By the end, you'll understand the story of matter, and it'll feel much easier than a textbook. Let's start with what an atom actually is. An atom is the smallest particle of matter that retains the properties of an element. At its center lies a tiny, dense nucleus containing protons, which carry a positive charge, and neutrons, which have no charge. Surrounding the nucleus are electrons, negatively charged particles that move in specific regions called energy levels or shells. The number of protons in the nucleus balances the number of electrons, making the atom electrically neutral. Our picture of the atom didn't appear all at once. First, John Dalton imagined atoms as tiny indivisible balls, like well-made marbles, each element having its own kind. Then J.J. Thomson discovered electrons and thought the atom was like a plum pudding, a positive blob with electrons stuck inside, like raisins in a cake. That changed when Rutherford did his gold foil experiment. He found most of the atom is empty space, and that all the positive charge is squished into a tiny nucleus, like finding a marble inside a huge, mostly empty room. Finally, Bohr refined that idea. Electrons don't just float randomly. They live in certain energy levels and can jump between them by absorbing or emitting energy, like stepping between rungs of a ladder. These steps brought us closer to the modern idea. A tiny nucleus with protons and neutrons, and clouds or levels where electrons hang out. Now that we know what's inside an atom, how do we tell one atom from another? That's where the atomic number and mass number come in. The atomic number is simply how many protons are in the nucleus. If you have 6 protons, that atom is carbon no matter what. The mass number is the total of protons plus neutrons in the nucleus. So if carbon has 6 protons and 6 neutrons, its mass number is 12, and we call it carbon-12. But you can have atoms of the same element with different numbers of neutrons. Those are called isotopes. They're still carbon because they have 6 protons, but their mass is different. Carbon-14, for example, has 6 protons and 8 neutrons. Chemically, they act almost the same, because chemistry depends on electrons and protons. But some isotopes are heavier or unstable. Unstable ones can be radioactive, meaning their nucleus slowly breaks down over time and gives off tiny bits of energy. That's how scientists can date old bones or wood using carbon-14, and how doctors use radioactive isotopes to see inside the body. When you look at the atomic mass on the periodic table, it's usually not a whole number because it's an average of all the naturally occurring isotopes, weighted by how common each one is. So, we've seen atoms and what makes them different. Now imagine lining up all the different kinds of atoms, elements, in a smart order so we can see patterns. That's the periodic table. It's like a giant map of elements, arranged by increasing atomic number, with elements that behave similarly are grouped together. When you move across a row, called a period, you're adding one more proton and one more electron into the same shell. That slowly changes how the atom behaves. When you move down a column, called a group, all those elements have the same number of electrons in their outermost shell, so they tend to act in similar ways. For example, the first column, Group 1, has elements like lithium, sodium, and potassium. They all have one electron in their outer shell and are very reactive. That repeating pattern, properties coming back again and again, is why we call it periodic. The table helps you predict things. If you know where an element sits, you can guess how it might react, whether it's likely to gain or lose electrons, or whether it behaves like a metal or a nonmetal. Inside the periodic table, we classify elements to make sense of them. There are broad categories like metals, nonmetals, and metalloids, and more specific families like alkali metals, halogens, and noble gases. Each of these groups shares certain chemical behaviors. Groups are the vertical columns. Elements in the same group have the same number of valence electrons, the electrons on the outermost shell that control bonding, so they react similarly. Periods are horizontal, and moving across a period changes the number of protons and electrons in a predictable way, which changes things like size and how tightly the atom holds onto electrons. So classification is just organizing based on patterns. It's like sorting animals by whether they fly, swim, or run, and then further by their leg count or diet. The periodic table does that for elements. Next big classification is metals, nonmetals, and metalloids. Metals are mostly on the left and middle of the table. They're usually shiny, They conduct heat and electricity well, and they can be stretched or beaten into shapes, like copper wires or aluminum foil. Metals tend to lose electrons when they react, forming positive ions. Nonmetals are on the right side. They're often dull, don't conduct electricity well, and can be brittle if solid. Think of sulfur or phosphorus. Nonmetals tend to gain or share electrons when they react. Then there are the metalloids, which sit along the zigzag line between metals and nonmetals. These elements, like silicon and boron, have mixed traits. They might conduct electricity a little, enough that we can control it. That's why they're used in computer chips and electronics. They're semiconductors. Now let's put it all together. Every object around you is made of atoms. The atom structure explains why some elements react and others don't. The atomic number tells you exactly what element it is. Isotopes explain small differences in weight, or why we can do cool things like carbon dating. The periodic table is your cheat sheet. Once you know where an element is, you know a lot about how it behaves. And when you look at metals, nonmetals, and metalloids, you understand why some materials are used for wires and some for insulating, and why silicon is the heart of electronics. Understanding atoms and how they're arranged is like learning the alphabet of chemistry. Once you know it, you can start reading and understanding the whole story of matter. Now that you know how atoms are built and organized, our next step is to see how they join together to make everything you can touch and see. Till then, share and subscribe Stellar Science Knowledge.